Welcome back again. We are reading this article called Electrically Tuned Fractional Order Temporal Differentiator in Silicon Photonics. Let me read the abstract again for review purpose. Here, full wave analysis and design of an electrically tunable optical fractional order temporal differentiator, that is a differentiator basically based on an ultra compact micro ring resonator, that is MRR, has been presented. Electrically tunability has been realized through free carrier dispersion. FCD means free carrier dispersion, that is popularly called plasma carrier dispersion effect in the resonator with PIN and PN junctions. So there is this PIN structure and PN structure in which we achieve carrier plasma dispersion effect, because these junctions are p-type and n-type material based. The first order optical diff is realized based on the critically coupled resonator without applying any bias voltage in the junctions. Also, fractional order differentiator with differentiation order alpha is greater than 1 is realized by overcoupled resonator with the forward bias PIN and PN junction. While fractional order differentiator with alpha is less than 1 is realized by undercoupled resonator with reversed bias PN junction. The high performance of design tunable optical differentiator and their high accuracy have been performed considering an ultra fast Gaussian input pulse with short full width at half maximum of 6.3 picosecond. So let us see what it is trying to tell. That first of all, there is a fractional order temporal differentiator based on an ultra compact micro ring resonator. So first circuit is this micro ring resonator, and this micro resonator has consists of PN, PIN and PN junctions. The first order optical differentiator is realized based on the critically coupled resonator without applying any bias voltage. So critically coupled resonator without bias any voltage junction. Okay, so first it is without bias. Without bias. Also fractional order with differentiator order alpha is greater than 1. So this fractional order differentiator with the alpha greater than 1 is realized overcoupled. That is called overcoupled resonator. Overcoupled resonator with forward bias PIN and PN junction. Both are in forward bias. While fractional order, so this is also fractional order. Fractional order, okay. Fractional order with the alpha is less than 1 is realized by undercoupled. So undercoupled resonator with reverse bias. MRR with reverse bias. So here MRR made of PN and PIN. So in one case without bias and fractional order differentiator having alpha is greater than 1, and in this is overcoupled resonator and alpha is less than 1. It is undercoupled micro ring resonator and the circuit is working in the reverse bias. However, whenever it is alpha is greater than 1, circuit is working in the forward bias overcoupled region. So this is all about. So this is all about our abstract. So microring resonator based on PN and PIN, and in one case without bias, other one is forward bias, fractional order differentiator, alpha is greater than 1, in which overcoupled resonator, and when alpha is less than that is the undercoupled microring resonator, which is working in the reverse bias condition. So this is in brief what is called your abstract. So I hope this is understood. Now we are moving, and we have read up to here mathematical modeling. So alpha order, and we are trying to look into this fractional order derivative. So alpha order fractional derivation of ft. So ft is your function, and we want to get it we want to get it fractional order differentiation. So this is dt, but it should be at fractional order. And now this function is being considered to take its Fourier transform, and the Fourier transform is given by this equation. So it can be written as I omega of order alpha and then f of omega. This is the Fourier transform of f of t. But there is extra term, that is I omega of power alpha. So now coming to fractional order, when this value is greater than 0 and value is greater than greater than 0 and less than 0. So these two values are here. So I omega is written, I think, here 2 pi f. Okay, so this portion I omega, I think, yeah, I omega can be further written as the transfer function of mathematical fractional order differentiator. So f of omega is simply straightforward. However, there is extra term that is called I omega of power alpha. And this is what is written as, this we are giving name as fractional order differentiator. So according to this, the transfer function of mathematical fractional order differentiator as an optical filter. Now we are realizing this fractional order transfer function of mathematical fractional order differentiator. So fractional order differentiator is being realized now as an optical filter, and it has some coefficients like this 2 pi f having power alpha and exponential of I alpha pi by 2 for greater than, and same here but only negative side, exponential minus I alpha pi by 2 into f. So where f is here omega minus omega naught divided by 2 pi is the baseband frequency, which is written here, and omega naught is the resonance frequency. So okay, so this is the baseband frequency we defined as omega minus omega naught divided by 2 pi. Otherwise, f is simply omega by 2 pi. So therefore, an alpha order temporal differentiator has an amplitude response of this. Amplitude response is now this one, and phase response of plus minus alpha lambda by 2. So the amplitude response is this one, that is called omega minus omega naught power alpha, and phase response is plus minus alpha pi by 2. This is the amplitude response, this is the phase response. Phase response, amplitude response. Now moving further, 2.2 photonic microring resonator. An all-pass MRR consists of a microring evanescently coupled to a single bus waveguides 1 to 12 and 23 to 25. Figure 1 shows the schematic of a designed ultra-compact silicon all-pass microring resonator based on PIN and PN junctions. Average radius of the all-pass MMR is 4 micrometer, while the air gap of 100 nanometer has been considered between the rings and the bus waveguide. Okay, so let us see figure 1. Here we can see figure 1. Here is figure 1. Yeah. Let us see first figure 1. Schematic of an ultra-compact silicon all-pass micro-ring resonator based on a PIN and PN. So figure 1 is a PIN. So you can see here radius R is from center to this. I think this is a ring. This is the actual ring R, and the gap between this ring and the waveguide is here 100 nanometer here gap. Now the inside there is another ring, green color, it is P dot, and the red color ring is a N dot. Now this voltage is supplied between P and N. Okay, in order to make it forward or reverse bias. Now coming to this PN junction, which again there is a ring. Okay, in PIN, since region between P and N should be intrinsic, so the silicon material is working as a intrinsic region. So this is P, this is I, this is N. So PIN. And here PN junction. So this earlier which was the ring, now it is a junction. So depletion junction. So inside we have P and outside we have N. So P N. And they are forming a junction here. Again, in both cases, the radius is 4 micrometer, gap is 100 nanometer between this ring and the waveguide. So structure is okay. Now let us see the figure 2. Transverse cross section of RRA and bus waveguide based on PIN and PN. So now this is a cross section here. So below they have this is the substrate of silicon dioxide. Above is a material of silicon, but silicon material is doped. This region is doped PN plus, and this is right hand side P plus. And this is, so this is here P, this is I, this is N. So PIN, and this is metal contact. And the waveguide is optimized for single wavelength, single mode, that is at 400 nanometer. And the height is 230 nanometer, which is the standard etching height. So 400 by 220 nanometer. And now 1 micrometer away from here, and 1 micrometer is away from here. So 1, 2, and 2.4 micrometer. So total this region is 2.4 micrometer. And here, okay, no problem. Now for this case, N type, so total this 400, I think this is in middle. So from here to here you can meet constant doping. I think we have to see whether it is constant or what. 50 nanometer is high, 220 nanometer is this, and this is P plus, and this is N plus. So PN junction, so this is contact 400. Right? So in order to have better plasma dispersion effect, sometimes this center is off from this junction is off from the center. This either the P side is more because holes has larger effect on plasma or refractive index. This is essential for changing the refractive index. Now moving to this figure 2 explanation wise. So we can see here shows the schematic of transverse cross section of all pass micro ring resonator considering PIN and PN junction. As we know, silicon photonics ring waveguide typically have very small transverse cross section with some micrometer dimension due to a large refractive index. Contrast, of. So the designed ring waveguide has dimension of 400 by 220 nanometer on top of a silica substrate with a thickness of 3 micrometer. In order to realize a high optical confinement, the slab has been designed with a small thickness of 15 nanometer. With the upper cladding is a layer of air. In the p-ion junction, the distance between doping area and the side wall of a ring is considered about 1 micrometer to reduce the overlapping of p and n plus region in the optical mode. The structure has been designed based on the silicon or insulator wafer to obtain the fabrication compatibility with CMOS technology. The micro ring resonator and the silicon bus waveguide can be fabricated using electron beam lithography and reactive ion etching. Then the N plus and P plus regions of the diode with uniform doping concentration of approximately 10 to the power 19 per centimeter cube can be fabricated using photolithography. Furthermore, the metal cap can be realized by lift-off techniques. Our design has been modeled by the numerical software, which calculates effective refractive indices of the guided modes and their associated field distribution by solving the electromagnetic wave equation using 3D FDGT techniques. Figure 3 shows the electric field profile EY of the fundamental TE-like guided mode well confined in the core of the waveguide. Its effective refractive index at the frequency of 193.098, that is 1552.54 nanometer, is 2.397. According to 12, the transfer function of A all pass RRA can be expressed by this. So transfer function is tau minus ART e to power minus j phi RT divided by 1 minus tau ART e to power minus j phi RT. Here tau is the field transmission coefficient and the of the coupling region. Also A of RT is equal to exponential minus alpha pi r is the round trip field attenuation factor in the MRR, and alpha RT, sorry, phi RT, this is C RT, this is phi RT, beta to pi r is the round trip phase. So first one is the round trip attenuation and second one is the round trip phase. R and alpha are the average radius of MRR and the propagation loss constant respectively. Assuming the coupling loss is negligible, the transmission coefficient tau is related to the coupling coefficient. Okay, coupling loss is negligible, that are related. So kappa through tau square plus kappa square is equal to 1, where kappa can be expressed as kappa is equal to pi by 2 multiplied by an effective S minus an effective A. So this is S and A are the effective refractive indexes of the symmetric and asymmetric modes between the MRR and bus waveguide respectively. So we have to see symmetric mode when two waveguides are there in the vicinity. So there is a mode called symmetric mode and asymmetric mode. The electric field profile of the mentioned modes and their corresponding effective refractive indices are shown in figure 4. So we can see here. So since this is a air gap of 100 nanometer, and this is suppose a waveguide of microresonnator here, like this. So this is a waveguide, this is a waveguide here, the two waveguides. So 400 nanometer we have seen, and that is also 400. So that is why, and the gap is 100 nanometer. So there is a symmetric mode, there is a asymmetric mode. That kind of situation has been shown here in my component. The intensity transmission and the phase response of a all pass microresonnator based on 3D FDGT simulation and analytical calculation for the transfer function of the APMRR. So this is here intensity transmission, and this is optical frequency here. Optical API MDDT, and this is analytical method. Both are following each other. And phase response is shown here, optical frequency versus phase response from 0 to 2 pi. You can see this is here delta phi. So both are analytical as well as optical MDDT. And you can see here intensity transmission, this intensity transmission phase response of APMR in its critical coupling region compared to the magnitude and phase response of mathematically differentiator with order of alpha is equal to 1. Now this is a critical coupling, exact coupling, 100%. 3 dB bandwidth. Okay. So here we have left. We're trying to see. Yeah. And we see the numerical and analytical results are in good agreement with confirm our proposed differentiator structure design. In order to investigate operation of the optical differentiator accurately, its results should be compared with those of calculated for the mathematical differentiator. Figure 6 shows the intensity transmission and phase response of the APMRR in its critical coupling region without applying any bias voltage in the PIN. Okay, so figure 6 shows that without applying any bias. In agreement with the magnitude of first order mathematical differentiator. The approximate value for the notch depth of the intensity transmission in the frequency response of 193.098 terahertz is minus 32 dB, corresponding to its mathematical differentiator counterpart, that is minus 50 dB. Obviously, the phase shift of pi in the resonance frequency confirm that APMRR works in the critical coupling regime. The phase response is very important to determine the order of differentiator, that is the phase shift in the resonance frequency divided by pi is equal to the differentiator order. Okay, that is very important. The phase response is very important to order of differentiator. The phase shift in the resonance frequency divided by pi. So how much phase shift in the resonance frequency divided by pi is equal to the differentiator order. Okay, so order is equal to the phase shift in the resonance frequency. Phase shift in the resonance frequency divided by pi equal to order. In addition, figure 7 shows that electric field at the output of a PMRR is near 0. This one. Electric field at the output of a 0. Okay, this is input here, output. This result is in agreement with the notch depth of a PMRR in the critical coupling region. Critical coupling, when light goes, it is just round, no output is coming. That is minus 32 dB. Accordingly, it indicates the first order differentiator of a constant function. Okay, first order. No shift. And the analytical results are in good agreement, which confirms our proposed differentiator design. In order to investigate property of the optical accurately, it's okay. It is okay. Now, electrical tuning. So before coming on electrical tuning, we conclude today's session. And we will come back again and start reading from the 2.3. So just we have to start it. Thank you for attending this session.